Hello, I am Dr. J D Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about the pipelining. So at the end of this video, the student will gain knowledge regarding what is pipelining process, how it is useful to improve the performance of the computer, what are the operations of the pipeline with examples. This topic learning outcome is mapped with the course outcome of summarize the concept of pipelining and inter-process communication for advanced processor design. The basic concepts that are discussed in this video are introduction, pipelining, what are the types of pipelining, arithmetic pipelining, and what are the conflicts of the pipelining. So parallel processing systems can be used by the advanced multiprocessor. So the parallel processing systems can capable of executing multiple instructions simultaneously. So they can provide simultaneous data processing tasks for the purpose of increasing computational speed of the computer system. When more than one task is executed in a overlapped fashion, so that number of instructions that can be executed for a unit of time can be increased, so that the computational speed of a computer can be increased with the help of parallel processing. Parallel processing systems are required to meet the demands of the large-scale computations. When the user is demanded for the large-scale computation or large-scale data processing, which is required for the engineering and scientific applications like the domains of artificial intelligence, seismic graph analysis, weather forecasting, aerodynamics, defense. In these areas, they require the large scale of computations. So when the user requires this large scale of computation, the parallel processing systems can be used to satisfy the user needs. So parallel processing has high level of complexity. Why? Because multiple instructions are to be concurrently executed. So to support this, more number of functional units, more number of registers can be required. So parallel processing system has high level of complexity that can be achieved by having multiplicity of functional units. So in a general computer architecture, we have basic functional units like input unit, CPU, output unit. The CPU is further divided into control unit, arithmetic and logic unit, memory unit. Only this single arithmetic and logic unit can capable of doing the processing of integer numbers, floating point numbers, logical operations as well as shift operations. But when multiple instructions can be executed concurrently, can require multiple functional units, so that each one can require to perform a specialized task. So this is the architecture of processor with multiple functional units. So apart from ALU, these units can have a specialized function and can be used to perform the specific task. So here adder subtractor is one unit, integer multiply is the second unit, logic unit, shift unit. So adder, subtractor, integer multiply can operate on fixed point numbers. So they are used to perform the addition, subtraction and multiplication of fixed point numbers. The logic unit can perform the logical or bit manipulation operations. Shift unit can use it to perform the shift operations like the logical shift, arithmetic shift and the circular shift operation. Incrementer can use it to increment the register values or the memory word content by 1. Next, to support the floating point operations, floating point adder subtractor, floating point multiply, floating point divide. So, the arithmetic operations performed on the floating point numbers can be supported with these three functional units. So, each and every functional unit can be used for a specialized task so that concurrently the multiple instructions can be executed in the parallel processing systems. So here the major performance measure of the computer can be the throughput. What is throughput means? The number of instructions that can be executed in a unit of time. So the purpose of parallel processing is used to speed up or increase the computer processing capability. So the amount of processing that can be accomplished during a given interval of time is referred as the throughput. So here with the multiple functional unit with parallel execution of instructions, the number of instructions executed per unit time is definitely increased with the parallel processing computer systems. So the amount of hardware can also be increased to support this parallel processing, which in turn increases the cost of the system. So with the parallel processing system, the throughput can be increased, which results in the performance of the system can be increased. But it requires more functional units so that the hardware requirement can be increased. Hence, the cost of the system can also be increased. So, how to model these parallel processing systems? For example, consider given computation can be divided into concurrent tasks for execution on a multiprocessor system. So here the processes can be divided into small tasks. So these tasks can be executed concurrently. So whenever this division can take an equal duration model, then this given task can be divided into n number of equal tasks, equal subtasks. So each of which can be executed by one processor. So the main task can be divided into subtasks. In case of equal duration model, each subtask can be used, can be executed with a equal limit of the time limit of the duration. If it all TS is the execution time of the whole task using single processor, then the time taken by the each processor to execute its subtask can be represented with a TM. So it can be the total time for execution of the whole task is TS. By how many subtasks the parts are there, TS by 1 is the time taken by each processor to execute a subtask. So the speed up factor is one of the most important factor that can be considered in the parallel systems. So these can be defined as the ratio between the time taken by a single processor to solve a given problem instance to the time taken by parallel system consisting of n processors solve the same problem instance. So this ratio can be referred as the speed up factor. So let us consider S of n is the speed up factor. So time taken to execute a task can be the TS by TM. So here TM is TS by n. So here TS by n, which is equal to n. That means how many subtasks are there? That execution can be done with a single task execution, that is thereby increasing the throughput in the parallel processing systems. So one of the technique which can be used to implement the parallel processing system is computer system that can be employed with multiple functional units, like for integer calculations one special functional unit, for logic shift operations, another functional units, and for floating point arithmetic, special functional units like that. And the another technique that can be used to implement the parallel processing is the pipelining. Now, what is pipelining? So, pipeline process is implementation technique where arithmetic sub operations are the phases of the computer instruction cycle overlap in execution. So, if at all a computational task is given that can be divided into subparts, these parts can be implemented in a overlapped fashion, or the phases or the steps of the instruction cycle can be executed in a overlap fashion by using the pipeline process. So, it is a technique of decomposing a sequential process into sub-operation. So, the major task can be divided into sub-operations. Each sub-process being executed in a special dedicated segment that operates concurrently with all other segment. So, the main task can be divided into subtasks. Each subtask can be executed in a special dedicated segment. So, these segments can be operated concurrently with other segments of the parallel execution of the task. So, a pipeline can be visualized as a collection of processing segments through which binary information flows. So, main task can be divided into subtasks, and these subtasks can be executed in a dedicated segment, and it can be concurrently executed with the other subtasks. So, we can visualize a pipeline as processing of this dedicated segment and where therein the binary information flows between these segments. So, a way of speeding up execution of instructions is the pipeline. And as a summary, the overlap execution of multiple instructions. So, concurrently, more than one instruction can be executed. Thereby, it is supporting the parallel processing systems with a technique of pipelining. What is the key idea of pipelining? So, here breaking the big computational task as a small pieces. So, each piece has to be stored and processed by using a pipeline register. So, it is faster for repeated computations. Pipelining increases throughput. So, here the big task can be divided as piece. Each piece can be executed with the help of pipeline register as a segment, and this segment can be concurrently executed with other segments, and the binary information flows between these various segments of a task. So, this type of processing can be recommended for the repeated computation or the looping processes, and which in turn increases the throughput of the system. So, here consider an example of pipelining, how it can be process the computational task. So, consider here the processing task, the processing computational task is two numbers can be multiplied and it can be added with the third number. A and B are the two numbers, they can be multiplied, and after multiplication, the product can be added to the third number C, and this can be achieved for a repetition computation of values 1, 2, 3 until 7. So, pipelining is the process which can be recommended for the repetition processing. So, here the first values can be taken by AI, BI, that is A1, B1, C1 can be implemented the task. Second, it has to consider A2, B2 and C2. In the third iteration, it can consider A3, B3, C3 like this until 7. The repetition of this computational process can be implemented. So, this task can be divided into small pieces, and each piece can be executed in a dedicated segment. So how these tasks can be grouped or divided into segment. So the sub operations performed at each segment can be, the first segment is loading the values, first number, second number into the corresponding registers. So the first number A can be loaded into the register R1. Next, the second number B can be loaded to the register R2. So this is the inputting of AI and BI. The first iteration can be, the I value can be 1. So A1, B1 values can be loaded to the registers R1 and R2 respectively. And this is the segment 1. And in the second sub operation, the values that is loaded into the register can be multiplied. So here R1 into R2 can be performed and this product can be stored in the register R3. At the same time, concurrently, the third number can be loaded into the register R4. So multiply and input C is the second segment operation. So this is the segment 2. And the third segment is the product that is stored in the register R3 can be added to the third number C that is loaded in the R4. So R3 plus R4, the addition can be performed and sum is stored in the register R5. So add Ci to the product is the third segment. So in the pipelining, the major task can be divided into pieces or sub-operations. Each sub-operation can be executed in a dedicated segment in the pipeline register, which can be operated parallelly with other segments. So here the task of AI into BI plus CI can be divided into 3 segments. During the segment 1, inputting the AI and BI to the corresponding registers, the second segment can process the multiply operation. At the meanwhile same time, the C value can be inputted. And in the third segment, addition, the third value to the product can be performed. So this task can be divided into 3 segments. So now with a flowchart, we have to describe how this pipeline process can be implemented. So here AI value can be first loaded to the R1, BI value is loaded to the R2. So this is the segment 1 operation. In the segment 2, the multiplication and inputting the Ci to the R4. So the multiplication, the product value can be loaded to R3. So this is the segment 2 operations. After product and inputting the third value, in the segment 3, the addition can be performed and this sum can be stored in the R5. So this is the segment 3 operations. So the major task of AI multiplied by BI plus C for the operations of 1, 2, 3 repetitions until 7 can be divided into 3 segments. And here in the first segment, the input to the registers can be performed. In the second segment, multiplication and the input of the third number can be performed. In the third segment, the addition and storing result to the register can be implemented. So this is the pipelining process. So how the content of the registers during implementation of the example A into B plus C during the pipeline process. So each and every sub operation can be implemented with the help of clock pulses that are generated with the help of the sequence counter of the control unit. So during the first clock pulse, the first segment of sub operation can be implemented. So here R1 and R2 values can be loaded to the R1 and R2 registers can be loaded with the two input numbers AI and BI. In the second segment, the first segment numbers that are A1 and B1 can be moved to the second segment operation during the second clock pulse, that is A1 multiplied with the B1, and loading of the C1, the second segment operations of instruction 1 can be performed. At the same time, concurrently, A2, B2, the second repetition values can be loaded to the registers R1 and R2. This is the segment 1 of the instruction 2. And in the third clock signal, these segment 2 can be moved to the segment 3 operation. So A1 into B1 plus C1, this is the segment 3 of instruction 1. And this segment 1 of instruction 2 can be moved to the second segment, that is A2 into B2 plus C2 can be performed. This is the segment 2 of the instruction 2. At the same time, the segment 1 of third instruction can be initiated. Okay. So if you observed here at this stage, 3 instructions can be parallelly or concurrently executing. So thereby the parallel processing can be supported with the help of pipelining example. So here at the same 3 clock pulses, one instruction can be executed, and the second instruction at the second segment stage, third instruction at the segment 1 stage, so that the number of instructions that can be executed per a unit time can be increased, which in turn results in increase of the throughput that helps to improve the performance of the system. So here, what are the general consideration during the pipelining process? For example, there are k segment pipeline with a clock time of TP seconds. With total number of n number of subtasks are there, those can be executed in T1, T2, etc. Tn are required to be executed. If T1 required the time equal to k into TP seconds, remaining n-1 task emerge from pipeline at the rate of 1 task per clock cycle. So they will be completed with the n-1 into TP seconds. So here the first task, if you consider it as k into TP, the remaining n-1 task can take t-1 TP seconds. So that total clock cycles required are k plus n-1. So consider here, if k is the 3 segment processor, so n is 5 subtasks, then 3 plus 5 minus 1, it can be the 7. So here these are the general consideration how the segments execution time has to be calculated in the pipelining process. And the behavior of the pipeline can be illustrated with a special diagram. The diagram is referred as space-time diagram. So it is a representation of segment utilization as a function of time. So the horizontal steps displays the time in clock cycles and vertical axis gives the segment numbers. So how the space and time diagram is looked into. So this is the example of space and time diagram. So here the horizontal axis can represent the clock cycles. The vertical axis can represent the segment. So here which clock cycle can operate on which sub-segment and what sub-operations during this time period can be executed is illustrated with the time-space diagram. So that it can shows the behavior of the pipeline at the given time. So at the clock tick 1, segment 1 has to be taken. So clock tick 2, segment 1 of second segment sub operation can be implemented. So the behavior of the pipeline can be visualized with the help of the space-time diagram. Now, what are the types of the pipelining? There are 2 types of pipelining can be available. One is arithmetic pipeline. Second one is instruction pipeline. What is arithmetic pipeline? Arithmetic pipeline are mostly used in high-speed computers. So parallelly, various arithmetic operations can be carried out with the help of the arithmetic pipeline. So they are used to implement floating point operations, multiplication of fixed point numbers, and similar computationals encountered in scientific problems. So here the pipelining can support the parallel processing computers. The parallel processing computers generally used for high performance computers. So there the major application domain is scientific and engineering application domains. These parallel processing systems can be used. So which involve the complex arithmetic operations of floating point operations as well as fixed point multiplication like this. So to these scientific problems and complex arithmetic operations can be implemented with the help of arithmetic pipelining. An arithmetic pipeline divides arithmetic problem into various sub-operations for execution in various pipeline segments. Just now we discussed one example, A into B plus C. This major task can be divided into 3 segments, and these 3 segments can be executed separately, implemented separately with a pipeline register in parallel with the other segments of the operation. Now consider another example, floating point adder pipeline. So here the example that can be considered is x is equal to a into 2 power a, y is equal to b into 2 power b. So for this, the numbers that can be considered are 0.9504 into 10 power 3, that is the x value. Y value is 0.8200 into 10 power 2. So these values that can be considered in this example. So here capital A, capital B are the two fractions. Two fractions that are represent the mantisas. The mantisas can be represented with a small a and b. So two numbers, the two floating point numbers are considered, x and y, and the capital A, capital B are the two fractions, small a, small b are the two exponents. So the example values that can be considered are 0.9504 into 10 power 3. The second y value can be 0.8200 into 10 power 2. So the combined operations of floating point addition and subtraction is divided into 4 segment operations. So each arithmetic operation can be divided into small pieces. So each segment contains the corresponding sub operations to be performed in the given pipeline. So how these major tasks can be divided into 4 segment operations? What are those 4 segments? The first one is compare the exponents by subtraction. Okay, the exponent values can be compared with the help of the subtraction. Align the mantisas. Third segment can carry out the sub operation of add or subtract the mantisas. The fourth operation is normalize the result. So the task of this floating point adder pipeline can be divided into 4 segments. The first segment can take care of the comparison of exponents. The second segment can take care of the aligning of the mantisas. The third segment is looking into the adding and subtraction of the mantisas, and the last one is normalizing the result. So how the first segment can be implemented? The first segment is compare the exponents by subtraction. So here the exponents value compared by subtracting them to determine their difference. With the help of subtraction, the comparing of the exponent operation can be take place. The larger exponent is chosen as the exponent of the result. So here we taken as in the example, the x value can have the 10 cube. So the exponent value is 3 for the x, and for the y value 10 square. So the exponent value is 2. So the comparison of multices has to be taken place with the help of subtraction 3 minus 2. That is the 1. So it determines how many times the multicy is associated with the smaller exponent must be shifted to the right. So this sub operation can be implemented as a segment 1 of the pipeline. And the segment 2 of the pipeline is align the multicies. So the multicy associated with the small exponent is shifted according to the difference of exponent determined in the segment 1s. So here 2 exponent has to be represented with the cubic value so that the multicies can be aligned. So here it is 10 square, 10 power 2 or 10 square. So to represent in the cubic value of the exponent, here after floating point a 0 can be added. So this sub operation can be implemented as a aligning the multicies. And the third segment sub operation is the 2 multicies are added in the segment there. So here x plus y value multicies, the values of 0.9501, 0.08200 can be added. The result can be here 1.0324 into 10 power 3. So this operation can be implemented as segment 3 sub operation of the pipeline. What is the segment 4? Normalize the result. So to normalization, the exponent value has to be raised by 4 so that it can be represented as normalized value 0.1324. So this normalization can be done as a segment 4 step of the pipelining, arithmetic pipelining. So how these segments can be implemented in parallel, that can be represented with a flowchart. So this is the flowchart of the floating point operations. So 4 segment operations can be performed here. So the floating point added subtracted can be divided into segment 1. So here comparing the exponents by subtraction is the segment 1. Segment 2 is choose the exponent. Segment 3 is align the multicies. Segment 4 is normalization. So how this can be parallelly executed. The exponent values can be represented as small a, small b. And the multicies can be represented as capital A, capital B. The segment 1 is comparing exponent by subtraction. So here the comparison of exponent small a, small b can be carried out. And depending upon the difference value, the align multicy, the second segment can be executed. So the multicy values can be aligned and can be stored as a in the register R. Next, depending upon that, the addition or subtraction of multicies can be performed. After addition or subtraction, the fourth segment operation is normalizing the result. So in this way, the task of floating point adder subtractor can be subdivided into 4 segment operations. So during these pipelining execution, some conflicts or drawbacks can be achieved. The first drawback is resource conflict. So if a segment is executing one in sub operation, the other segment can require the same resources, then the resource conflict can be occurred. In the similar way, 2 segments can sharing the same common data dependency problems can be arises. and if at all branching is occurring, so the updation of PC values can be done properly with the sub operations. So this encounters the branch difficulties. So these are the three major conflicts that can arise during the implementation of the pipeline operation. What are the resource conflict? So these resource conflict caused when two segments access the memory at the same time. So this problem is resolved with the separate instruction and separate data memories. So the resource is the major resource that can be used during implementation of pipelining is the memory. If the same memory segment can be needed by the two segments for execution, then this resource conflict can be arises. So this problem can be resolved by employing separate instruction and separate data memories. The second conflict is data dependency. Data dependency occurs when an instruction depends on the result of previous instruction. So this data dependency, one instruction or one segment during execution depends on one data that can be used by other segment, but it is not available during that time. So the operand access to memory is delayed until required data is available. So three techniques that can be used to resolve this situation is hardware interlocking. So the common items, if they are used by segment 1, with the help of hardware, a lock can be provided. Whenever the utilization of the data item is completed, the lock can be released so that other segment can be used it. Next, operand forwarding. With the help of special hardware mechanism, the identification of data dependency can be carried out, and if at all any situation of conflict arises, the operands can be forwarded so that the operation can be smoothly executed. Next one is delayed load. So here also the detection mechanism can identify the conflict of the data dependency with the special hardware, and the load can be delayed so that the operation can be wait for some time until the required data can be available, so that the data dependency conflict can be resolved. So the three techniques can be used to resolve the data dependency conflict, that is hardware interlock, operand forwarding and delayed load. Next, the third conflict is branch difficulties. So these branch difficulties arises from branch instructions. The branching can generally alter the execution of the program sequence conditionally or unconditionally. So to resume to the major program execution, the PC value can be properly saved. So the instruction that modify the value of the PC during these branch instructions. So during this time, the branch difficulties can be arises. So the techniques that can be used to handle branch instruction difficulties are prefetch target instruction, branch target buffer, loop buffer, branch prediction, delayed branch. Prefetch target instruction. So the target instruction address can be stored in the separate register and can be used to resume the main program execution. Next is branch target buffer. A special buffer can be used. BTB register or buffer can be used to store the branch address. Next, loop buffer can also be used the special register hardware component to store the target instruction address value. So branch prediction, a hardware can be implemented to identify the branch difficulty, and the address can be saved in the special register to resume the correct sequence of program execution. Delayed branch also used to store the special hardware mechanism for the detection of branch difficulties and storing the return address or the PC value with a special registers. So by using these techniques, the branch difficulties can be resolved. So the major difficulties in the pipelining can be resource conflict, data dependency conflict, and branch difficulties. With the help of these special techniques and hardware mechanisms, these conflicts can be resolved. So two types of pipelines are available. One is arithmetic pipeline. Second one is instruction pipeline. Arithmetic pipeline, how it can carry out the major arithmetic operation with small sub operations concurrently, that can be illustrated with an example in this video. And what are the different difficulties that can be used, that can be arised during pipeline execution, how they can be resolved with the special hardware technique that can be discussed. The another type of pipelining is the instruction pipeline, that will be discussed in the next video. And the references that can be used in this video are the M. Morris Mano Computer System Architecture, a textbook, and the second textbook is the William Stallings Computer Organization and Architecture, and the third one is the web resource for the development of this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.